computational frameworks. After completing this lesson, you will be able to describe the role of computational frameworks, explain MapReduce concepts, explain Yarn framework and concepts, describe MRv2 on Yarn, explain configuring and understanding of Yarn, describe Yarn applications, describe Yarn memory and CPU settings. In the previous lessons, you have learned about Hadoop cluster setup, its framework, architecture, how it works, how a cluster is set up, and how data is managed in a Hadoop cluster. Once data is loaded in the cluster, it needs to be processed. In the first topic of this lesson, you will learn about the frameworks for processing data in a Hadoop cluster. Computation frameworks are execution engines responsible for executing data processing tasks on Hadoop. Some of the available options to process data on Hadoop clusters are the well-established MapReduce framework, the relatively newer Yarn framework, and open-source tools in Hadoop ecosystem. Open-source tools include Hive, Pig, Spark, Cascading, Crunch, Tez, Drill, Impala, Presto, and so on. Some of these frameworks work on top of other frameworks. For example, queries written in Hive can run on MapReduce or Tez. The image shows the categories of processing frameworks and tools or frameworks within a Hadoop ecosystem. Let's learn more about these categories. Hadoop processing frameworks can be classified into general-purpose processing, abstraction, SQL, graph processing, machine learning, and real-time or streaming frameworks. General-purpose processing frameworks allow users to process data in Hadoop using low-level API like MapReduce or Spark. Abstraction frameworks allow users to process data using a high-level abstraction. API-based, custom DSL is typically built on top of general-purpose processing framework. SQL frameworks allow users to query data in Hadoop using SQL. It can be built on top of general-purpose framework or as a special-purpose framework like Impala. It can also be considered abstraction framework. Graph processing frameworks enable graph processing capabilities on Hadoop. It can be built on top of general-purpose framework, such as Giraffe, or a special-purpose framework like GraphLab. Machine learning frameworks allow users to perform machine learning analysis on Hadoop data. It can be built on top of a general-purpose framework like Machine Learning Library, MLlib, on Spark, or on a standalone special-purpose framework like Oryx. Real-time streaming frameworks provide near real-time processing capabilities for data in Hadoop ecosystem. It can be built on top of a generic framework, such as Spark Streaming on Spark, or on a standalone special-purpose framework such as Storm. Processing frameworks can also be classified based on architecture. Some frameworks have active components such as server, client, services, and so on. These can be considered engines like Hive. Some frameworks do not have any active component and can be considered libraries like MLlib. With variety comes the possibility of making choices. Making appropriate choices depends on the use case, requirement, available expertise, and experience with the framework. Hadoop's ecosystem is evolving. Therefore, using only one framework for processing data is no more an option. Adopting more than one framework is an industry choice and also demands efficient resource management decisions within or across clusters. All frameworks implement shared nothing architecture, also known as harding. There are no shared resources to cause bottlenecks in an architecture in distributed systems where each node is independent of other nodes. Hadoop's processing framework uses distributed HDFS storage. Data is not shared, and each node processes a unique subset of data. Shared nothing architecture offers high scalability, fault tolerance, no single point of failure, and fast recovery. The general-purpose processing framework is always needed. Because other frameworks only solve a specific use case and may not be sufficient to handle all processing needs of an organization. Common frameworks in this category are MapReduce and Spark, TES, or other newer frameworks. MapReduce is the most mature and also the slowest. MapReduce is the framework which is typically installed, has higher overheads, less flexible in comparison to other frameworks, and many frameworks rely on it. Spark, TES, or some newer frameworks like Apache Flink can be used without having to install MapReduce, and thus do not have the overheads of running map and reduce. Spark provides faster processing due to in-memory computing. Let's look at some features of MapReduce and Spark. MapReduce and Spark have different APIs. Unless an abstraction framework is used, migrating from MapReduce to Spark necessitates rewriting of jobs in Spark. Spark provides high-level processing APIs. The time and code required to write a Spark job is a lot less than for a MapReduce job. TES is well suited to building abstraction frameworks rather than building applications. Abstraction and SQL frameworks reduce the time spent on writing jobs directly for general-purpose frameworks. The common frameworks in this category are Pig, Crunch, Cascading, Hive, and Impala. Pig, Crunch, and Cascading are abstraction frameworks. Pig can run on MapReduce, Spark, or TES. Apache Crunch provides a higher-level API that can be used to run MapReduce or Spark jobs. Cascading is also API-based and can run on MapReduce or TES. Hive and Impala are SQL frameworks. Hive can run on MapReduce, TES, and Spark. Special-purpose SQL engines, such as Impala, Presto, and Apache Drill, aim at faster SQL. The features of abstraction and SQL framework are time savings by not implementing common processing tasks using low-level APIs, possibility to change the underlying general-purpose frameworks when needed, avoids code changes whenever framework changes, which might be required in case of direct coding on general-purpose frameworks, reduced overheads for running an equivalent job on general-purpose frameworks, faster running of query through Impala or Presto, as they use a different, specialized execution model. Special use cases need special frameworks like graph, machine learning, and real-time streaming frameworks. Let's take a look at these in the next few screens. Giraffe, GraphX, and GraphLab are popular graph frameworks. Giraffe is a library that runs on top of MapReduce, while GraphX is a library for graph processing on Spark. GraphLab is a standalone, special-purpose graph processing framework that can handle tabular data. Mahout, MLlib, Oryx, and H2O are commonly used machine learning frameworks. Mahout is a library on top of MapReduce, while MLlib is a machine learning library for Spark. Oryx and H2O are standalone, specialized machine learning engines. For near real-time analysis of data, Spark Streaming and Storm are the most popularly used frameworks. Spark Streaming is a library for micro-batch streaming analysis on top of Spark. Apache Storm is a special-purpose, distributed, real-time computation engine. Here are the images of the different frameworks described on the previous screens. In the second topic of this lesson, you will learn about MapReduce. MapReduce is a programming model for developing applications and processing large datasets in parallel. Hadoop version 1 popularized MapReduce as a programming model and a processing framework for batch processing of large datasets. However, it has some drawbacks. It is more I/O intensive, which means that it involves a lot of I/O overhead. It is not suitable for interactive analysis and constraints when support for graph, machine learning, and other memory-intensive algorithms is needed. Hadoop version 2, with the advent of Yarn framework, allows for interactive analysis and specialized processing. This places Hadoop in a dominant position as a big data analysis platform. Yarn brings significant performance improvements to some applications, supports additional processing models, and implements a more flexible execution engine. We will discuss the Yarn framework in detail in the next topic. MapReduce is the programming paradigm that allows processing and generating large data sets. It can even process and generate massive scalable data sets using a parallel distributed algorithm on a cluster. MapReduce is Hadoop's computation framework for processing parallelizable problems across large data sets using the nodes in a cluster by dividing workload across a cluster of machines, thus allowing scalability to larger clusters. Immutability of data elements in MapReduce ensures that any change in input does not reflect in input, but occurs by generating temporary intermediate output for further execution. MapReduce consists of two phases, mapping phase and reducing phase. Let's take a look at each of these on the following screens. The mapping phase is taken care of by a mapper function. This is the first phase of the MapReduce program, where a list of data elements are provided to a function called a mapper. A mapper transforms the input data elements into a list of output data elements. Mapping phase and reducing phase. The reducing phase is taken care of by a reducer function. This is the last phase of the MapReduce program, where values are aggregated. A reducer function receives an iterator of input values from mapping phase. It then combines these values together, returning a single output value. Let's take a look at the overall picture of the MapReduce flow. Each value has a key associated with it. The reducing functions works on a list of data elements, i.e., the key value pairs, to produce one output value or a list of output values. All the output values are not reduced together. The values with the same keys are processed together by a single reducer, as shown in the image. Here, different colors represent different keys. In mapping, several instances of mapper are created on multiple nodes in a cluster. Each instance receives a different input file. Driver is a component of MapReduce that initializes the job, instructs Hadoop platform to execute the job on input, and controls where the output is placed. In reducing, several instances of reducer method are also instantiated on different nodes, which work on the data generated by mapper, reduce it, or sum it to generate a final output value. Inputs typically come from input files loaded on HDFS. The files are split and stored in blocks, and the blocks are evenly distributed across nodes. The mapping phase involves running map tasks on many or all nodes of a cluster. Any mapper can process an input file. It loads the set of files that are local to the system and processes them. After completion of the mapping phase, intermediate data or the key value pairs are exchanged between nodes to send all the values with the same key to the same reducer. Reduce tasks are spread across nodes in the cluster, same as mappers. Map or reduce tasks do not communicate with each other. Reduce generates output locally, which is part of a consolidated output on HDFS. Now, let's understand the intermediate phases in MapReduce. There are 5 intermediate phases in MapReduce. Mapper. The mapper performs the user-defined work of the first phase of MapReduce. It works on a key and value. Map method emits key and value pairs to be further processed by reducers. A new mapper function is assigned for every map task that works on every chunk of data. Partition and shuffle. The process of moving map outputs from completed map tasks to reducers, while other map tasks might still be under process, is known as shuffling. A different subset of intermediate key value, called partitions, is assigned to each reduce node. Sort. Each reduce task is responsible for reducing the values associated with several intermediate keys. The set of intermediate keys on a single node is automatically sorted by Hadoop before they're presented to the reducer. Combiner. Combiner optimizes the bandwidth usage of MapReduce. It is optional and runs between a mapper and a reducer. It is a mini-reduce process that operates only on the data generated by one machine. Reducer. A reducer instance is created for each reduce task. This is an instance of user-provided code that performs the second phase of MapReduce. For each key in the partition assigned to a reducer, the reduce function method is called once. This receives a key and the values associated with the key. These values are returned by an iterator in an undefined order. Running a MapReduce job in Yarn cluster from terminals and using Web UI to look at the output. Now that you have seen how to check the configuration properties for MapReduce in Yarn, you will see how to run a job in the cluster from the terminal. You can see the cluster is already running, so to check or revisit the configuration files, you will have to log in first as root by typing sudo su and giving the password in the terminal. After logging in as root, you will find the config files in /etc/hadoop/conf. Now, look at the configuration properties set in MapReduce-site file. You need to type vi/etc/hadoop/conf/mapreduce-site.xml. As you can see, these are the properties which are specific to MapReduce, and this will govern the running of your job. For example, you can look at some configuration properties which describe what kind of compression will be followed, whether it will be at block level or at file level. You can also know the compression codec which will be followed. You can understand if you are following any compression for the intermediate output, which comes from a map phase. As you scroll down, you can look at other properties, such as how many reducers will be used by a particular job, which in this case shows 3. As you are not going to make any changes here, type Q! And you will come out of the properties. Now, to run a MapReduce job, you need to be a user who has access to run MapReduce jobs and access to write data to the HDFS. By default, every user does not have access to the cluster. So, here in Cloudera cluster, HDFS is the default ID which has admin access over the cluster. Now you will log in as HDFS by typing in su-hdfs. Type hdfs dfs-ls/ and you can see different directories which exist. As you can notice, HDFS is the superuser. Now, if you look in the user directory by typing in hdfs dfs-ls/user, there are subdirectories for different services which are set up. For every service, you have a username that is the same as the service name, which is the owner of the cluster. So you can submit jobs using HDFS. You can search for the jar files, which will have your programs, by typing ls/opt/5.8.0-1.cdh-5.8.0.p0.42/lib. Within lib directory, there are many other directories, so type ls/opt/cludera/cdh-5.8.0.pzero.p0.42/lib/hadoop-mapreduce. As you can see, this is where you have the jar files, and you will select one jar file out of these. Now type Hadoop, and you will get different options which can be given with Hadoop, and one option is jar. Type Hadoop jar /opt/cloudera/parcels/cdh hyphen 5.8.0-1.cdh 5.8.0.p0.2/lib/hadoop-hadoop-mapreduce/hadoop-mapreduce-example-2.6.0-cdh 5.8.0.jar and hit enter. Now you can see the different programs which are available in the jar file. As you can see, one of the programs is word count. Now if you type Hadoop jar /opt/cloudera/parcels/cdh hyphen 5.8.0-1.cdh 5.8.0-lib/hadoop-mapreduce/hadoop-mapreduce-example-2.6.0-cdh 5.8.0.jar word count and hit enter. You will be asked for an input file and an output location. If you look at the cluster by typing hdfs dfs-ls/data analysis platform, Yarn brings significant performance improvement. 5.8.0-1.cdh 5.8.0-lib/hadoop-mapreduce/hadoop-mapreduce-example-2.6.0-cdh 5.8.0.jar word count and hit enter. You will be asked for an input file and an output location. If you look at the cluster by typing hdfs dfs-ls/, you can see there is a directory named My Data. Now type hdfs dfs-ls/mydata, and you will be able to see some files, and you can use any of these files. Let us check in the user directory by typing in hdfs dfs-ls/user. Now you can see many subdirectories like Hue, HDFS, History, and Hive, and so on. You can get the input file from the local machine, or you can create your own file and run a word count on that. To create a file, type cat >file2.txt. Now you can enter the data into your newly created file as shown. Now press Ctrl+C. To look at the contents inside the file, type cat file2.txt. Now you can write this file to HDFS, for which you will need a directory where you can write it. Let us copy the file, file2.txt, to HDFS. For this, type hdfs dfs-var/lib/hadoop-hfs/file2.txt/mydata. To check if the file has been copied to the HDFS directory, type hdfs -ls/mydata. You can see that the file2.txt has been copied. You can now run a MapReduce on the file2.txt file. For this, type Hadoop jar word count /mydata/file2.txt/mydata/output1 and hit Enter. After processing the file, you can see the details of the MapReduce job, which you have now run. The total input paths to process is 1 because you have subjected just one file for processing, and you are using one block. As it is a very small file, the number of splits is 1. You can see the job ID is in the running status. Also, you can see the submitted application ID. You can also see the URL to track the job for the particular application. So, per MapReduce, every line is considered a record, which you can see under MapReduce Framework. As you can see, the map input records shows value as 2 because you just had 2 lines in the file. The map output records show 13, which represents the word count. The reduce output records also show 13, which also refer to the word count. Also, you can see the CPU time spent is in milliseconds. You can also look at how many mappers and reducers were used for the job in the launched map task and launched reduce tasks. To look at the output directory, type hdfs dfs-ls/mydata. As you can see, the last directory is output1, which you have created. Now type hdfs dfs-ls/mydata/output1, and you can see these success files, which denote that the job ran successfully and has multiple part files. Each part file specifies the particular reducer which was used by the job. To get information about the output file, type hdfs dfs-cat/mydata/output1/part-r-00001, and you can see the word count. 3 different reducers were used to work on the data. They broke down the records into key elements and counted how many times a particular word occurred in the file. To check the status of the job, you can use the browser. First, select the machines. In this case, you have selected machine M1. After this, you need to pick up the public IP of the machine where the name node is running by copying the IP address. Now you have to paste it into the address bar. This will take you to the login page for the Cloudera Manager page. Now log in as admin with the appropriate password. After completing the job, you can see there are 2 critical health issues. To rectify this, you have to restart the services. Now click Cluster, choose Cluster 1, click Actions, and select Restart from the options, and you can restart all the services. Now click Yarn, then Web UI, and select the Resource Manager Web UI, IP 10.0.147. As this is a standby machine, you will get a prompt as standby and redirecting to active one. If you come across any problem due to IP not resolving, you can give a public IP directly from the web interface. For this, go to the cluster, click Web UI, and select Resource Manager, Web UI, IP 10.0.149 and choose the Active Resource Manager. Now in the All Applications page, you can see the job which you have submitted as the first and recent entry. You can also see that it has been submitted by the user HDFS. It is a word count program. The application type is MapReduce. It has run in a default queue, the status as shown as finished, and succeeded, and it has a history tract. Now, click the job ID. You will be able to see the job status and tracking URL, which is history, and also what kind of resources and how much resources were used. Click History, and you can see the page is not loading. So, you need to go to the EC2 Management Console page and select the second machine, which is M2, and copy the public IP from there. Now, paste this public IP into the address bar of the browser and hit Enter. Now you will be able to see the job history details. In the job history page, you can see some properties such as job name, queue used, node, logs, task type, which were run, and attempt type. Now click Counters, and you will see the detailed information. There is information about CPU time in milliseconds, which in turn will have details about the breakup of the map and reduce phase and the total time. You will also get information about how many map input records were processed, the result of map output records, how many bytes were read, how many bytes were written, were there any errors when the shuffle phase was happening, and so on. Click Configuration, and you can see the different types of properties that have been set in the config files, which may directly affect the MapReducer. When you look at the dfs.block size, it shows the block size as 128 MB. So, if one or many properties affect the job run, then you can go into the Configuration tab of Yarn and make the changes in MapReduce related files, restart the service, and then you can run the job. Click Map Tasks, and you will be able to see how many map tasks were run. Now, click on the Task ID, which will show you the attempt, the machine, and the logs, and so on. This is how you can browse the job which you have run. As you can see, there are many jobs that were run successfully, and you will get all these informations from the Job History Server, which collects the information and records the history of jobs which have been run on the cluster. To look at the job output, click Cluster. Choose Cluster 1 and click Hue, then Hue Web UI, and now you will get the Hue login page. Click File Browser, and now you can write data to the cluster. Click the directory to navigate to the desired directory. Click My Data directory to view the particular files which you have loaded. Now click Output 1 to see the output. You can also update the data to the cluster by clicking Upload and choosing the tar file zip/tgz/bz2 file. Now for the prompt, Upload and extract in /mydata. You need to click Select zip, tgz, or bz2 files. Click Downloads and select the appropriate file. So now the tar file which you have selected will be uploaded. Select the tar file which was uploaded, which is Scale Data. Now click Scale Data, and this will show you a directory and a text file. Click the Scale Data directory, and you will see the subdirectories. You can click on any of the directories and see the information. You can run a MapReduce on this job and do a word count. Now, let us see how Hue provides an interface to look into the job. Click Job Browser, which will take you to the page that shows all the jobs that were run. The first on the list is the most recent job, which is the one we ran using the MapReduce. Click the job ID of the job. Now you will be able to see the container that was used. Click on the container to see the log files. In the syslog tab, you will be able to see what happened in the job and which staging directory was used to store the intermediate data. Click back in the job browser and then click on Tasks. You will be able to see different map and reduce tasks. Click Metadata to see the information about the job and the different properties affected by the job. Click Counters, and you will get information about the job and the Java classes that are used, such as org.apache.hadoop.mapreduce.jobCounter. So in this demo, you have learned how to run a job in the Hadoop cluster. In the third topic of this lesson, you will learn about Yarn. Yarn stands for Yet Another Resource Negotiator. It is a resource management layer for Apache Hadoop ecosystem, where, unlike in MapReduce, the resource management capabilities and the processing engine are separated. Yarn is like an operating system on a server. It is designed to allow multiple user applications to run on a multi-tenant platform, capable of managing and monitoring workloads, implement security controls, and manage high availability features of Hadoop. Let's look at the type of hosts in Yarn cluster and resources on the following screens. A Yarn cluster contains two types of hosts: Master, Resource Manager, and Worker, Node Manager. A resource manager is the master daemon that communicates with the client, tracks resources on the cluster, and coordinates work by assigning tasks to node managers. A node manager is the worker daemon that launches and tracks processes spawned on worker hosts. Yarn defines two resources. They are vCores and memory. vCores, or virtual CPU cores. It refers to the virtual portion of the CPU core of a particular machine. Memory. It refers to the random access memory of worker nodes. The node manager tracks its own resources and advertises its resource configuration to the resource manager. The resource manager keeps a record of the cluster's available resources and hence knows how to allocate resources when requested. Now, let's understand the basics of the Yarn framework. A container is a request to hold resources on a cluster. A container holds requests consisting of vCores and memory, as shown in the image. The node manager launches a process, called a task, once the request hold is granted on the host. The task runs as a process inside a container. An application is a Yarn client program comprising single or multiple tasks. For every running application, a special piece of code called Application Master helps coordinate tasks on the cluster. This code runs as soon as the application starts. Let's understand the execution flow in Yarn on the next screen. The application starts and talks to the resource manager for cluster. The resource manager makes a single container request on behalf of the application. The application master starts running within the container. The application master requests other containers from resource manager, which are then allocated to run tasks for the application. Tasks always communicate with the application master. After completing the tasks, the application master stops running within the container, and the container is deallocated from the cluster. Then, the application ends. Let's take a look at pictorial representations of the execution flow. This image shows application, application master, and tasks running in multiple containers within a cluster. According to the MapReduce framework, an application consists of map and reduce tasks which can align themselves to Yarn tasks. These tasks run in containers on worker nodes in the cluster. Yarn components manage cluster resources and ensure the completion of tasks and applications. Now, let's understand the basics of Yarn configuration. There are two types of Yarn allocation: ideal and realistic Yarn allocation. In ideal Yarn allocation, a Yarn cluster can be configured to use up all the resources on the cluster. In realistic Yarn allocation, all the resources cannot be allocated to Yarn due to overheads of non-Hadoop related services running on nodes, operating system and utilities, custom programs, and so on. other Hadoop-related components that might need dedicated resources and should not share resources. Distribution-specific services, such as Cloudera Manager agents, in case of CDH cluster, and Hadoop-specific roles. Resources for HBase slave daemon region servers, if HBase is set up, and resources required for queries execution and so on, if Impala is set up. Once resources are allocated to components, the rest can be allocated for Yarn. Properties for Yarn cluster are specified in Yarn configuration file yarn-site.xml. It is a new config file introduced in Hadoop version 2 with the advent of Yarn Framework. Let's look at a snapshot of Resource Manager Web UI and understand cluster metrics on Yarn allocation. Assume there are 50 worker nodes. Yarn-related configuration properties: yarn.node-manager.resource.memory-mbi is 90000 and yarn.nodemanager.resource.vcores is 60. Memory will be given as 50 multiplied by 90 gigabytes, which is equal to 4,500 gigabytes. 4,500 gigabytes is equal to 4.5 terabytes. vCores will be given by 50 multiplied by 60 vCores, which is equal to 3,000 cores. On the next few screens, let's look at some important configurations. The table lists the configuration category and their respective resource limits. Please note that if the minimum container memory and vCore request is larger than the memory available, then Yarn will be unable to satisfy this request. The table lists the restrictions and considerations for container values. The map task memory property is mapreduce.map.memory.mb, and the reduced task memory property is mapreduce.reduce.memory.mb. These tasks run within a container. Their value should be less than the maximum size of the container. The property yarn.app.mapreduce.am.resource.mb is used to set the memory size for the application master. Since the application master uses a container, the property should be less than the container maximum. Looking at configuration properties for Yarn and MapReduce. Now that we have set up a cluster and learn how the cluster works, we will look into the configuration properties of Yarn, which include MapReduce. First, you must click on the Clusters tab and show Cluster 1. This will show all the services that are set up on the cluster. Click on Yarn, which will show the components in Yarn service. You can see the heading Yarn MR2 included, which means MapReduce version 2 is also included. Click on Configuration, which will show all the configuration properties. Here, we have three types of filters: Scope, Category, and Status. Under Scope, click on Yarn. You will find all the configuration properties. Under all the properties, you can see yarn.admin.acl, which is the access control list. ACL allows any user to be the admin of Yarn cluster. You can also check whether a resource manager has high availability using rm-ha cluster ID. You can see the details of the path of Yarn under System Users Home Directory. Now, you can select Node Manager, This is the path where the node manager stores the intermediate data. You can click on the question mark to understand a particular configuration property. Now, check in Resource Manager. This will contain the information related to the master, which governs processing. You can see that the fair scheduler is selected, and you can give the allocation files, which talk about minimum or maximum files that can be allocated to the cluster or pools that are created. Below that, there is Capacity Scheduler, through which you can define different queues and the capacity that should be allocated. Then click on Category. If you click on Ports and Addresses, you can find all the default ports that will be managed by Resource Manager, Scheduler, Resource Tracker, or the HTTP port. Then select Resource Management. This will display all the configuration properties of Resource Manager. This talks about CPU shares, memory, minimum-maximum limit, heap size, and so on. You can click on Logs to view all the log-related information. Information about Resource Manager log, the type of information collected, and the size of the log. You can also click on Advanced for additional information. If you change the information in this tab, you will be asked to restart the service. The changes will be incorporated after the service is restarted. Other than Admin Console, you can check the properties from the terminal by logging in as root. Then type ls/etc/h*, which will show you the different directories. If you are looking for processing, type ls/etc/hadoop/conf, and then type vi/etc/hadoop/conf/yarn-site.xml to check all the properties which were seen in Admin Console. In Admin Console, once you save the changes and restart the services, the changes are reflected in the config files. When you type /opt/cladera/parcels/cdh/lib/hadoop/etc/yarn-site.xml, you can find the same configuration properties that are related to configuration framework, that is, Yarn and the properties related to MapReduce. Finally, type vi/etc/conf/mapred-site.xml. This has properties that are specific to MapReduce, which runs on Yarn framework. Here we can see all the configurations related to MapReduce. This brings us to the end of the demo on configuration properties of Yarn and MapReduce.